Monday, we're going to do a vector escape room. All right, so unit vector. So the next thing we need to talk about. Unit vectors are a vector that are 1 unit in length. Okay, so a unit vector is a vector that has length 1. Okay, like our unit circle had a radius of 1. Our unit vector has a length of 1. You can take any vector and shrink it down to a unit vector using the following formula. 1 over the magnitude, which is the length of the vector, times the vector itself. Okay, so it'll give us a vector that goes in the same direction, but now only 1 unit in length. Okay, so for example, let's say I wanted to find a unit vector that was in the same direction as v, which is negative 12, 5. Okay. Remember when you see vectors, you might see them written like this, well, actually, I'll show you the other way in a minute. Just leave it like that for now. It's good. All right, so the first thing that we need to do is calculate the length of vector v. So we're going to think of 12 and 5 as legs of a right triangle, and when we're calculating the length, we're trying to figure out what's that hypotenuse. So it's just square root of both legs squared, so you really don't even need the negative. It's going to be positive anyway. Negative 12 squared and 5 squared, which is going to give me 144 and 25, which is going to give me rad 169, and that gives me 13. And we don't have to worry about a plus or minus when we take the square root because we're calculating a length, and length is always positive. Okay, so if I want to calculate the unit vector, 1 over the magnitude of the vector times the vector itself will look like the following. 1 over the magnitude of the vector here is 13 times the vector itself, which is negative 12, 5. When we have a vector, we always have these like pointed parentheses kind of to tell us it's a vector rather than just a coordinate. But you saw in the video yesterday a lot of same properties as if it was a parentheses. We're just distributing that 13 through. So the unit vector ends up being negative 12 thirteenths and 5 thirteenths. If there was like a radical, you just want to make sure you rationalize, but that's your final answer. If you wanted to check that it was a unit vector, that you did it right, you could calculate the magnitude of that. So you could use the Pythagorean theorem with those two numbers, and the magnitude should equal 1 if you've done it correctly. So that's a quick little thing you can always type in your calculator. Okay, so that's a unit vector. All right, there are 2 special unit vectors. They are called I and j. I is the unit vector 1, 0, and j is the unit vector 0, 1. So pretty much I is the unit vector that goes 1 unit to the right, and j is the unit vector that just goes 1 unit up. We can take any vector and write it in terms of I and j. So if we have like 3 i's, that would be the vector that goes 3 to the right, or negative 2 j's would be the vector that goes 2 down. Or if we start adding and subtracting them together, we get ones that go in the diagonal directions as well. So in general, let's say I had the vector, I'll just give you an example, 3, negative 4. Okay, so that vector goes 3 to the right and 4 down. If I wanted to write it in ij form, it would just be 3i, 3 to the right, and then minus 4j. It's negative, so it goes down, and then 4 down. Okay, so just another way to write a vector. See I, it just means the first unit, the horizontal unit. See j means the second unit or vertical unit. Any questions there? Little I here is not to be confused with I, imaginary number. That's something different. I and j are going to be bolded when you see them. That's how you know it's a vector rather than just, our imaginary numbers that we're used to or another variable. All right, so calculations that you saw in the video yesterday can be done in ij form as well. Yes, question? Not with vectors. There will not be. We're going to see imaginary numbers with polar coordinates a few sections from now, but right now, no. Okay. All right, so let's say we've got these 2 vectors. So vector u is negative 3i plus 2j, and vector v is I, or 1i, plus 4j. All right, so you can write them like this, or you could write them in the other form. So like u, I could also just say is negative 3, 2. And j, I could say is 1, 4. And if you write them in that form, in that standard form, you can calculate them the same way you saw in the video yesterday. If you want to keep them in ij form, though, this is what the calculations would look like. So let's say I wanted to do 3 times vector u plus 2 times vector v. 3 times vector u would be negative 3i plus 2j, plus 2 times vector v is I plus 4j. This is literally just like algebra 1 stuff. We're distributing and we're combining like terms. That's all you're doing. Okay, so if I distribute, I have negative 9i plus 6j and 2i plus 8j. And then I can just add my like terms together. So I'm going to end up with negative 7i plus 14j, which is equivalent to if you wrote the vector like this, negative 7, 14. Okay. Letter B there. If you see the magnitude bars, I would pretty much just ignore them to start. It's always going to be your last step. Okay, so we're going to calculate v minus 4u, and then at the very end, whatever that vector is, we're going to take the magnitude of it, find the length of it. Okay, so v minus 4u would look like I plus 4j, then minus 4 parentheses u. So negative 3i plus 2j, just filling in those two vectors for v and u. Distribute my negative 4. So I'll have 12i minus 8j, and then combine my like terms. So I'm going to end up with 13i minus 4j. Okay. Then at the end, I want to find the magnitude or the length of that. Okay, so that 13i minus 4j, again, you can think of it as 13 negative 4. That's the other way we would write that in that standard form. Think of those as legs of a right triangle. We're trying to find the hypotenuse, so it's just our quick little Pythagorean theorem with 13 and negative 4. So square root of 13 squared and negative 4 squared, which is 169 and 16, which is rad 185. And I don't think that one reduces, so we'll just leave it. Okay, so if you see the magnitude bars, just one extra step to find that length. Okay. Any questions on that one? Okay. All right. Another formula that you need to know about vectors. You're going to notice a lot of these formulas, they're pretty quick and easy little guys. You just kind of have to know what we use them for. So we can write a vector with just its horizontal and vertical components, v1, v2 with the little pointed brackets. We can write it with i's and j's, like we just practiced in unit vector terms. Or the third way we can write a vector is we can write it in terms of its length and an angle. So this is where the trig stuff is going to start to really show up now, okay? So angle of rotation tells us which direction our vector is going to be pointing. So if I can tell you which direction it's pointing and I can tell you how long it is, its magnitude, that's enough to describe what a vector is. And this is the formula, okay? So again, like I said, trig functions are coming in. All right, the first thing is just the magnitude or length of the vector. We know that. Then the new guy that shows up, we see our i's and j's, we recognize those. The new guy that shows up here is theta. The angle theta is called the direction angle. So you might see it tell you the direction angle is. And it is the angle that starts on the positive side of the x-axis. Where else have we seen angles that start on the positive side of the x-axis? On the unit circle. Right? Okay, so that theta is like your unit circle angle. Okay, so we're going to start on the positive side of the x-axis, rotate counterclockwise. So if I'm between 0 and 90, my vector's in quadrant 1. If I'm between 90 and 180, I'm in quadrant 2, so on and so forth. So we're going to see a lot of stuff we already know kind of coming back into play with this formula. All right, everybody have it written down? right, so let's do an example. Write the vector that has magnitude 2 that makes an angle of 11 pi over 6 with the positive x-axis. They're telling us the magnitude. So magnitude, we'll just call it vector v, is 2. And they're telling us that theta is 11 pi over 6. All you have to do is fill it in. Vector v, then, is the magnitude, 2, times. Now, when you look at the formula, you'll notice cosine is first and sine is second. Cosine goes with I, sine goes with j. Where else have we seen that cosine comes before sine? On the unit circle, okay? So not something you should have to memorize. We know cosine comes before sine. Cosine is horizontal, sine is vertical. So cosine 11 pi over 6 goes with I, that's horizontal. And then sine 11 pi over 6 goes with j, that's vertical. And then we can simplify this. What is, from your unit circle, the cosine of 11 pi over 6? Rad 3 over 2. I. What is the sine of 11 pi over 6? Negative a half, which I don't even really need the plus there, but that's fine. And then finally, to simplify that, I just distribute my 2 in. So we end up with rad 3i minus 1j, or just minus j. You can write it like that, or you can write it like this. Rad 3 negative 1 would be that vector. So it depends what MathXL is asking for. It might just say IJ form. Sometimes they call it like a system form instead of IJ form. I'm trying to think how else MathXL might word that. Or they just might say standard form, which is your little pointed brackets. Okay. Questions on that one? All right. Find the direction angle for this vector. 2i minus 3j. I'm going to draw a picture. So remember, these angles, whether it's IJ form or standard form, they always, this vector always starts at the origin, okay? And then from there, when we see 2, negative 3 in front of my I and j, that means 2, negative 3 is the terminal point. It's where that vector stops. So we can plot that point. 2, negative 3 is, you know, down in quadrant 4, it's going to look something like that. 2, negative 3 is that end point, okay? Our job is to find the direction angle. We can turn this picture into a unit circle picture that we recognize. Remember dropping the altitude to the x-axis, our little reference triangles, okay? And I can label sides then. 2 is across, negative 3 is down. My job is to figure out the direction angle. So from the positive x-axis, rotated counterclockwise. If I want to find theta, I'm going to first find alpha, or whatever you want to call it, x, inside the triangle there, okay? So what trig function could help me find alpha? Sine, cosine, or tangent? It's just right triangle trig right now. This is just tangent. Tangent of alpha equals, and you actually don't even need the negative here. If you use the negative, it'll give you a negative answer. If you use the positive, it's going to give you a positive answer. You're going to use the positive answer anyway. So I'm just going to say 3 over 2, opposite over adjacent. And then in your calculator, you need to do the inverse tangent. We want degrees here. Okay, so make sure you're in degree mode. If I do the inverse tangent of 3 over 2, I'm going to get 56.3 degrees to the nearest tenth. Okay. How are alpha and theta related in this picture? And the picture is going to change depending on what quadrant you're in. How are alpha and theta related? Or how can I get theta from alpha? What would you do? Yep, Angela. Just 360 minus that angle. So that's going to give me 303.7 degrees is the direction angle. Okay, so make sure if it's asked for a direction angle, whatever angle you have makes sense with what quadrant you're in. This vector is in quadrant 4, so you better have an answer, you know, at the beginning between 270 and 360. It's in quadrant 4. Any questions on that? Okay. You could also solve for the magnitude here if you needed to. You just do the Pythagorean theorem with 2 and 3. All right. So now, our really fun word problems. Okay. So we know how to write a vector in a bunch of different ways. And we know how to draw them, and we know how to add and subtract them. So all these little pieces now we're going to put together with applications of vectors. So a vector is 2 things. It has a force of some kind, a strength. It could be like a speed. It could be, pounds per inch. You're pushing something. And then it has a direction that thing is happening, speed that you're driving in or direction that you're pushing something, okay? When we have multiple vectors added together, it means multiple forces are acting on an object at the same time. And the resultant is the result. It's the vector that tells us what's actually going to happen when all of these forces act on one object all at the same time. So for example, let's say I take this desk and I start pushing it towards up, okay? And then Ella's like, I don't want you to push the desk towards me. So then she is like, I'm going to push the desk towards the window. Okay, so I'm pushing this way, Ella's pushing this way. Where's the desk going to go? Is it going to go there? Is it going to go there? Where's it going to go? It's going to go there. Okay, that's a sum of 2 vectors. And who's ever pushing harder, the desk is going to move more in their direction, right? Like if I push harder, it's going to go more that way. If Ella pushes harder, it's going to go more that way. Does that make sense? A little bit? Okay. And we could have 3 or 4 people pushing this desk. We could have 3 or 4 vectors that we're adding together to figure out what's actually happening. All right, so now we're going to draw some pictures of that actually happening. All right, so it says find the magnitude and bearing. Bearing is where it's actually going to go. Of the resultant if 2 forces are acting on an object. Force 1 is a 40-pound force, so that's like our magnitude. That's its strength. And then it's acting northward, and force 2 is 30 pounds force acting westward. All right, so a nice pretty picture here. Just going to draw my axis. Okay. Both vectors are going to start at the origin when I draw them. Force 1 starts at the origin, and it's going north. There we go. And its force was 40 pounds. Its length is 40 from start to finish. Okay, and that is F1. Force 2 is going to the west, and he's going to be a little bit shorter because he only has 30 pounds of force. Got it? Yes? Good? Okay. So what we need to do is we need to be able to add these vectors together, and when I add them together, I get R, the resultant vector, which is where this object, whatever it is ultimately going to go. To get that, we're going to use this formula. A vector is the magnitude of the vector times the cosine of its direction angle I plus the sine of its direction angle J. All right. So for vector F1, its magnitude is 40. What's its direction angle? If I go from the positive x-axis and I rotate counterclockwise, how far do I have to rotate to get to F1? How many degrees? 90 degrees. Plus sine 90J. All right, what's the cosine of 90? 0. And then what's the sine of 90? 1. So this vector ends up being, and I'm just going to write it in this form, 0, 40. And remember that coordinate, kind of, if I think of it as a point, is the end of this arrow. Does it make sense that the end of that arrow would be 0, 40? If I plotted that, right? Okay, can you guess what this one's going to be if I do it? Yeah, it's going to be negative 30, 0. If you did a direction angle for this one, it would be 180. But these nice pretty ones where we can see and we can actually count because it's left, right, up or down, we can just name what the vector is. That's the vector negative 30, 0. Starts at 0, 0, ends at negative 30, 0. Okay? All right, so now I want to add F1 and F2 together. You're just adding the horizontal components, which are kind of like, they look like our x coordinates. and our vertical components, which look like y coordinates. If I add 0 and negative 30, I get negative 30. And if I add 40 and 0, I get 40. That's your resultant. Let's plot the resultant. The resultant will go, start at the origin, and go 30 to the left and 40 up. Does that make sense? That that's where that object's going to move, that where the desk is going to move, right? Isn't that what we talked about? Okay. So now the question is, we have the resultant. We want to find the magnitude of the resultant and the bearing of the resultant. Okay, the magnitude of the resultant is just the length, which is our quick little Pythagorean theorem, negative 30 squared and 40 squared, which is going to give you just 50. Okay. Magnitudes in this problem are pounds of force, so that's what I'm going to label it. So this object is going to move with 50 pounds of force. As far as a bearing goes, a bearing is different than a direction angle. Can you guys tell me, is the resultant moving what direction? North, south, east, west, or a combination of the two? Okay, it's moving north, west, for sure. You can see that in the picture. We just need to figure out how far northwest. When we say northwest, it means from the north to the west. That's the angle that you're calculating right there. Okay. If I want to get that angle, let me make my nice little pretty right triangle. I know 30 is that side. I know 40 is this side. Can you figure out what the angle inside the triangle is? Well, alpha. How do I find alpha? You just did in the last problem. What trig function is going to help me? Tangent. Tangent alpha, like I said, you don't need the negatives, is opposite over adjacent, 40 over 30. If you do the inverse tangent of 40 over 30, or 4/3, you're going to get 53.1 degrees. How is alpha related to theta in this picture? They're what minus? 40. Not quite. It's 90 minus. They add to 90 in this picture. So they're complements. 90 minus 53.1, which is going to give me 36.9 degrees. Okay, and those are the two things that we need. So we add our vectors together after we write them as vectors to get the resultant, and then the resultant, that vector gives us the magnitude and the bearing that the question is asking for. Make sense? Okay, let's do one more. This will be our last one. Well, maybe. Might do two. We'll see. Okay. Find the resultant of the following system of forces acting simultaneously. So we have vector u. Vector u is 200 pounds of force in the direct, or it could say speed, 200 miles per hour, in the direction of northeast, 40 degrees. Vector v is 300 pounds, 70 degrees northwest. And vector w is 400 pounds, southeast, 20 degrees. 3 vectors. Draw the picture. Definitely going to help you to kind of visualize what's happening here. Excuse me. I'm going to try to color code this for you. All right. I'm going to start with vector u. Vector u is 200 pounds, so its length is 200, and it's northeast 40 degrees. Again, that means from the north to the east, 40 degrees. So this direction, that's 40 there. That's vector u. Vector u is 200 long. I'm actually just going to use that right now before I move on to my other vectors to calculate vector u. All right, what is the magnitude of vector u? That's the first part of the formula. The magnitude is, what does magnitude mean? Length. What is the length of vector u? 200. And then which trig function comes first? Cosine. Is 40 degrees a direction angle? It is not. What's the direction angle from the positive x-axis to get to u? 50. All right, and this is where we need a calculator. You're going to do 200 times cosine 50, and you're going to do 200 times cosine sine 50, sorry. And then you're just going to write your two coordinates. I'm going to write it in this form. You could leave it with i's and j's if you want to. All right, if I do 200 cosine 50, I'm going to give it 2 decimal places, 128.56. And if I do 200 sine 50, 153.2. 1. All right, and remember that kind of symbolizes what the end point of that vector would be. I know at least for sure from this picture, it better be in quadrant 1. Both of my components better be positive because my vector ends in quadrant 1. All right, take a minute, work together if you want to. I want you to do the same thing now. Add to this picture vector v and vector w, and then I want you to add them together to get r. Once you have that, stop, and we'll finish the problem together. Okay, so find vector v, find vector w, add them together to get r. Go ahead. All right, let's see. You should have a resultant vector of negative 16.54 and negative 120.06. If you didn't have that, double check your v and your w, and I would guess the most common mistake is going to be the angle, the 160 and the 290. If you didn't get them right, check your angles from that positive side of the x-axis, rotate counterclockwise. It's an easy thing to mix up there. After that, it might just be a calculator mistake. Yes?
Why aren't the angles just 70?
Because how the formula is, it's always a direction angle. If I plug in 70 and 20, and I take the cosine and sine of those numbers, it's always going to be positive. It's always going to give me a vector in quadrant 1. Right? Okay, so we have to use the direction angle, which is a similar angle, that's the same reference angle, but it gives us those negatives and puts it in the appropriate quadrant, putting it in the right direction. Okay.
290 and 160.
Okay, so I'm always thinking, like if I want to get to vector v, I'm starting here and I got to think about how much do I have to rotate to get to v. So the 160, I'd have to add 90 plus another 70 for that one. Or down here, I'd have to add 270 plus another 20. So it just depends what angle you're given, what direction you're given. That's why the picture really helps for that.
I did. It was 70 and 20. Got the same answer and just added the negatives in based on.
You can do that. Yes.
I think that's allowed.
That is because they have the same reference angles. That will work every time. Just make sure you remember.
Yeah.
Yeah, that's fine. Okay. Any questions? All right. Now let's finish it up together. Okay. So what quadrant is R in? R is actually in 4, is where this object will ultimately move. All right, so let's see, negative 16, if I'm under a little triangle here with it, negative 16, 120, it's gonna be like down there somewhere. 16.54 is that side, and 120.06 is that side, and that's R. Okay, that's a little tiny. Two things we have to find are the magnitude of R. I don't need the picture for this one. That's just my Pythagorean theorem. You can see it here. It's just the hypotenuse of that triangle I drew, if you want to visualize it. Add them, square them. Again, I don't need the negatives. Take the square root. 16.54 squared plus 120.06 squared. Take the square roots. I get 121.19. And again, it's pounds of force. We get out for that one. Okay. Then the other thing I need to find is the bearing. What direction is this vector going? North, south, east, west? South, west. Your job is to figure out how far, southwest. From the south to the west, that's theta. Okay, that's what we're trying to figure out. To find theta, we need alpha. Alpha is the angle in the triangle. What trig function do you think we're going to use to find alpha? Tangent. It's going to be the same thing over and over again. Tangent alpha is opposite 120.06 over adjacent 16.54. And again, you can include the negatives, but it's not going to make a difference. inverse tangent of 120.06 over 16.54, I get alpha is equal to 82.2 degrees. And again, you can see that alpha and theta, just like the last problem, are complements of each other. So if I do 90 minus that, I'm going to get 7.8 degrees southwest is the bearing of the resultant. Okay. Last part of this question, you may see a question that asks you, what force can be added to this system of vectors to create equilibrium? Equilibrium means, what do we have to do to the desk? How do we have to push it? And what direction do we have to push it so it doesn't actually move? There could be 7 of us all standing pushing this desk, but it doesn't move. That's what equilibrium is. It's the vector 0, 0. That's equilibrium. It is the resultant. Nothing happens. If I want to find equilibrium, all I have to do is find the opposite of R. R is where it's going to go. Negative R, the opposite of R, is where I want to push it back. Okay, so that is, in this case, 16.54 and 120.06. And then you could find the magnitude of that on its own. That's in quadrant 1. The magnitude of that is actually the exact same thing, 121.19 pounds. And the direction is actually the same direction, but the opposite way. So it's 7.8 degrees northeast, if you calculate it, instead of southwest. All right? Yes?
What do you do after you find alpha, the 82 point?
So you can see in the picture, alpha and theta add to 90. So it's just 90 minus to get that one. All right, I think we're good on these. The last problem, I'll just show it to you, but we won't do it. You might see a problem on Math XL that talks about like planes flying. It's the same kind of question that we just talked about. The speed of the plane is the magnitude. It's the length, okay? And then the direction, same sort of thing. It'll ask you for the bearing of the plane. It'll talk about like the wind in the plane and how the plane actually moves when it's affected by the wind. But it's the same sort of setup. You can draw it the same way as the problem that we just did. Okay? We might even make that like a warm-up problem. Okay. I think we've done enough, don't you, for today? Okay. All right. 7-4 Math XL is due on Thursday night. It's a longer one because of these couple problems at the end. I mean, not like long in like number of problems, but these couple at the end take a minute. All right, so try to get a few done each day. We only have 4 more Math XLs, guys. That's it. We're almost there. All right, I'll do cell phone lotto, and the last 10 minutes are yours if you're gonna want to work on your homework here. Okay.